speculations on test time scaling. Say what you will about OpenAI, they make iconic graphs. This graph is from the GPT-3 paper. It's one of several different graphs that demonstrate as language model parameters get larger, the models perform better at zero-shot tasks. This graph, and many others like it, has occupied the interest of the language modeling community for the last 5 years. It really changed the way we think about many different problems and how we build, design, scale, and invest in models. In fact, right now, it's safe to say that there are nuclear power plants being built just to support this graph. Recently, OpenAI released a new graph. Given the impact of their previous ones, I take this pretty seriously. In this graph, on the left-hand side, we see a curve that looks pretty similar to the curve we've seen before. In this curve, we see that more training time compute leads to consistently better accuracy on a hard task. On the right-hand side of this graph, we see a new curve. This curve looks similar in that we're seeing compute contrasted with the performance of the model. What's different is that this curve is showing test time compute. And what we are seeing is the performance on this task get much better as we add more test time compute to the system. This is new. We haven't seen this before in language modeling, and it's a topic of great interest. Before we dive into this topic more, it's worth noting what these problems actually look like. Well, they're pretty hard. We're not just doing retrieval or things that look a bit more like pattern matching. We're doing full-on reasoning in technical mathematical problems. One essay that often comes up when discussing these sort of scaling challenges is the bitter lesson. You've probably read this blog post before, but it's worth giving you a sense of what it's saying and how it applies to this problem. The bitter lesson is based on the historical observations that AI researchers have often tried to build knowledge into their agents. This always helps in the short term and is personally satisfying to the researcher. But in the long run, it plateaus and even inhibits further progress. And breakthrough progress eventually arrives by opposing approaches based on scaling computation by search and learning. I bring it up today because it's been a popular conversation among researchers in this space. What we've seen for the last 5 years is increase in the learning capability of models. What we might be seeing now is a move towards search. And in particular, a type of search that is facilitated by learning to allow us to scale on some of these more technical problems. In preparing this talk, I also watched some of the recent talks by Noam Brown, one of the contributors to this system. One thing he recommended when talking about his past work is he said that the most important lesson is that I and other researchers simply didn't know how much of a difference scaling up search would make. If I'd seen these scaling results at the start of my PhD, I would have shifted to researching search algorithms for poker much sooner, and we probably would have gotten superhuman poker bots much sooner as well. While he's talking here about game playing, the goal of his conversation is to encourage the field in general to think more about search. One of the other papers he brings up is a paper I found to be very influential around people in this area, even though it's not more widely known. This is a paper from 2021 that discusses scaling laws for board games. In this setting, it's easy to move back and forth between more training and more test time search. And in the paper, they describe how these two terms relate to each other. In particular, in these curves here, they show that there is a trade-off, that with more training time in the model itself, you can learn better systems. But that this alone doesn't replace the test time compute. By plotting these 2 points together, you can understand the relative relationships between these two and learn how to actually apply them in practice. When talking about similar techniques for language models, people often bring up a paper from OpenAI from 2021. In this paper, they're going to train what we'll call a learned verifier. To do this, they will use a generative model to produce hundreds of different solutions. They'll then have experts look at these solutions and select which are right and which are wrong. Using this information, they can then train a verifier. This verifier will tell you if you're doing well on the problem and can be used at test time to try to improve your answers. While there are a lot of details to the paper itself, one of the most important results is they show that searching against this learned verifier can lead to improvements even upon just training on the actual good answers themselves. In this graph here, the orange line shows the accuracy of the model that is running against the verifier compared to a model that's just trained on the trajectories themselves. This is an argument for moving beyond the standard supervised fine-tuning, or SFT, more to a system that utilizes a learned verifier in order to inject new signal into the model. This allows you to utilize that verifier to improve the model at test time. As we'll see, we don't think this is exactly what OpenAI is doing, but it gives you a sense of how they were exploring early uses of test time compute in developing their systems. And actually on that note, we really know very little about what is going on in OpenAI. In fact, I'm not going to really focus too much on trying to predict what they actually are doing, but I'd like to use the release of this model as an opportunity to provide a survey about what's going on in the open research field. In this talk, I'll give a survey of the public literature related to OpenAI's O1. As part of this process, I also took the opportunity to call up a lot of different researchers in the field. It's a nice perk of being a professor that a lot of different people will talk to me. And for this talk, I talked to about 25 different people about what they think is going on. Finally, I will include some rumors from social media. I'm not going to weight these too highly because who knows what's going on in practice, but that will give us some constraints for thinking about what the system could be doing. The talk itself will have 4 more parts. First, we'll talk about some of the clues behind what O1 might be. Then I'll provide some technical background behind the techniques that are actually used in these systems. Finally, I'll discuss 4 different suspects, why I think they're interesting, what papers have been written about them, and whether or not they might be what's going on. Finally, I'll end by talking about some implications for researchers or open source practitioners in this area. To gather clues, let's start with OpenAI's own words. In a blog post published with the release of O1, they wrote a lot about this topic, but much of it is mostly just marketing. There are 2 sentences, though, that give us a sense about what might be happening. First, they say, our large-scale reinforcement learning algorithm teaches the model how to think productively using its chain of thought in a highly data-efficient training process. This sentence gives us 3 clues into what might be happening. The first is that the system is using reinforcement learning. The precise definition of reinforcement learning has become quite hard to pin down, and it means different things to different people. I'm going to adapt the most loose definition and just say it requires some signal from some sort of verifiable problem. We're going to assume we don't have supervised data, and we need to acquire the signal in other ways. Secondly, the method uses chain of thought. Specifically, it's using chain of thought as its method of increasing test time compute. What this means is that we're not doing any sort of search during test time. In fact, the system is just generating a very long output stream and using that to make its final prediction. We'll discuss this more throughout the talk. Finally, the system is data efficient. What this means is that it's learned from a relatively small set of data examples. This is not making any claim about compute efficiency or even parameter efficiency, just that the amount of actual problems it needs is relatively small, where relative here is compared to, say, training on the entire internet. In addition to this sentence, there are several other assumptions that people seem to be making about these models. The first is that it is a single final language model that generates an extremely long and coherent chain of thought. Just to make that clear once again, it's just a model that babbles to itself until it thinks it has good enough information to make a guess at the answer to your hard problem. Second, we assume the model is not following from expert examples. This is not to say there isn't a huge amount of human supervision. It's just that that supervision is not given in the form of direct human answers to questions. It's not copying along with what humans did. Finally, there's an assumption that the behaviors it exhibits are learned. That means they come somehow from data or self-play, but not from being given to the model explicitly. Of these assumptions, the most important one is this idea of chain of thought. Let's describe what this means informally, and then we'll dive into a bit more of a formal explanation later in the talk. The informal definition is that the model is going to generate intermediate steps in the process of producing an answer. These intermediate steps are not supervised, but are simply sampled from the language model as we go. So in this example on the right, we are given a question written in red, and then we produce 4 steps of chain of thought written in green below. Each of these steps computes some intermediate term in the process. Finally, we produce a final answer at the end, which is used to evaluate our performance on the problem. In the same blog post, OpenAI highlights this use of chain of thought. They say O1 learns to hone its chain of thought and refine the strategies it uses. It learns to recognize and correct its mistakes. It learns to break down tricky steps into simpler ones. It learns to try a different approach when the current one isn't working. It's hard to pull too much signal out of this sentence, but it really highlights that chain of thought is where the action is happening. Unlike other systems that build in complex search as part of their test time, this model is simply utilizing the chain of thought to do these steps as it goes. In their blog post, OpenAI additionally included some examples of the chain of thought for the system. You're not actually able to see this chain of thought in the model they released, but we can look at some of the chains they provided. First off, we can see the chain of thought for a programming problem. Just to note again, this is something the model itself produced in the process of solving the problem. What we can see is that the model has produced an outline of all the steps it would like to produce. The outline is numbered and includes complex sub-steps. If you read the rest of the chain of thought, you can see that it's following this outline in the process of producing its answer. In another example, there's a form of rudimentary planning. We can see that the system is aware of the time constraints it needs to answer the problem. It also is able to stop and propose different options and choose which of these it would like to follow. While this is all in English, it's using cues like first or option 1 in order to specify the intermediate steps. Another ability that we see in these chains is forms of backtracking. So in this example for a math problem, it describes some intermediate term that it might need to compute. It then stops in the middle and says, well, actually, this may not help us directly. This allows the model to go back and determine that it might want to say something different. Again, this looks a bit like search, but it's not actually being performed with traditional search. It's simply the model talking to itself in order to determine the answer. A final ability we see is something like self-evaluation. Here we see it say, let's analyze each option. It then specifies the options it might want to consider, and it asks itself, is that a good explanation? The answer is a bit informal. It says, and then goes on to the next option itself. But again, this is an ability that can be used by the model in order to explore different possibilities and determine which ones might make sense. So in summary, chain of thought here is providing our method of test time scaling. While the actual words in the chain of thought look like search and planning in a classical sense, this is not actually being run at test time for the model. How does it learn to do this? Well, this is the big mystery. They claim that reinforcement learning is needed to induce this behavior. The rest of the talk, I want to explore how this might actually come about and look at some of the papers in the literature which talk about how you can get models to learn to do something like this, such that you can scale their test time compute. To get there, though, we're going to need some technical background. So for this section, we're just going to focus on formalizing this idea of chain of thought. We're not going to do any learning, but simply talk about what it means to start from a question, go through, say, 4 or 5 steps of intermediate reasoning, and then come up with an answer. Formally, we'll assume our problem specification is called X. This is just the question being asked that we need to solve. Our final solution will be called Y. This will represent, say, the conclusion or answer to our math problem. In between, we'll look to produce a series of steps, Z1 through ZT. These are not individual words, but instead full steps on the way to produce our final answer. We'll abstract a bit away from the fact that this is a language model and just think about it producing steps along in this chain. The final goal at the bottom of this slide is to produce a distribution over answers Y conditioned on our input X. This distribution is defined by taking an expectation over these latent chain of thought steps Z. As a warm-up, let's consider how standard chain of thought is done. We can't actually compute the expectation over all possible intermediate steps. So instead, we run ancestral sampling. This is a fancy term that just means let the language model generate until it produces an answer. Specifically, we'll sample T steps Z, these are represented by the green dots in the little picture, until we get to an answer Y, represented by the dot on the right. We can think about the amount of test time compute being applied here as T, where that represents each one of the intermediate steps on the way to our answer. In general, I use these graphs on the right to demonstrate how the chain of thought is being used in these processes. Many papers have noted that there is a way to get better answers to these problems. Instead of taking a single chain of thought and using it to produce the answer, we can instead sample n chain of thoughts. Once we have these n different chain of thoughts, we can take a majority vote in order to determine the majority answer. In this diagram here, each one of these chain of thoughts is sampled independently, and then we do some sort of normalization. The answers that are most common are the ones we decide. This provides a strong baseline and a way to utilize more test time compute to slightly improve our answers. You can obviously do this to a large extent, but people have found that it doesn't lead to some of the amazing results that we're seeing in the O1 blog post. The second piece of machinery we need is a verifier. Explicitly, we'll assume that we have an automatic verifier, but we only have it at training time. We'll define this automatic verifier as taking some answer y and telling us if it is wrong or right. This verifier might be, say, regular expressions to check that we've solved a math problem, or it might be something more complex like full-on unit tests for code. Again, just to make it clear, we don't have this at test time, but we are going to utilize it as a way to provide training signal for us to produce a better model. Throughout this talk, I'm going to assume that we have an automatic verifier. This is a common assumption in much of the research, and I think it's a reasonable assumption for solving these problems. That being said, it's not clear whether OpenAI is actually utilizing automatic verifiers or whether they're using learned verifiers. In some of their papers, they explicitly try to learn verifiers for some technical problems. Their argument is that this can produce more general-purpose models, and it's a way for them to utilize their large annotation facilities in order to improve their models. In the case of learned verifiers, there are some interesting research challenges. For instance, one challenge is that with a learned verifier, if the generator produces, say, crazy solutions, sometimes the learned verifier gets confused and accepts them. In this graph on the right, they show that for a math problem, the model will continue getting better, but then it will plateau and even get worse as they take more samples. They discuss how this is a challenge with a learned verifier, and I have to assume they've collected a lot of data and thought about this problem a lot more in recent years. However, since we're poor both in GPUs and in data annotations, we'll focus instead more on the automatic verifier situation. Once you have a verifier, there are many new things you can do. One idea is to do rejection sampling. This is a way of getting some distribution of chain of thoughts that yield correct answers. We're going to do this just by sampling again n different chains and simply keeping the ones that are verified. In my notation on the right, on the top picture, we see all the different samples that we picked. And then on the bottom picture, we see the chain of thoughts that led to correctly verified solutions. I'll use this little square box on the right to indicate which solutions were successfully verified. This process may be extremely compute intensive, but it gives us a way to get some of the good chain of thoughts that lead to the verified solutions. We're going to assume for now that you can plausibly get some solutions using this procedure, although it's not obvious for hard problems that this will ever yield a correct answer. The other thing we can do is to apply the same process, but starting from an intermediate step in our chain. So in this example here, we've run 3 steps of chain of thought, and from there, we'll do what's called a rollout. This rollout is the same as rejection sampling, but it just starts from an intermediate place in our process. This can be used to tell us how good we are doing from any step in the chain. It's not guaranteed to always work for good problems or bad problems, but at least gives us a direction in which to move in our system. Given this formal background, we now come to our main goal. We would like to learn a model that can take into account these latent chain of thoughts. We can write this down explicitly as a maximum likelihood problem, where we're interested in learning the model that performs as well as it can at producing verified solutions. We can then think about this as marginalizing out over all possible chain of thoughts that lead to the correct answer. Of course, this problem is combinatorially extremely difficult. We can't, with even nearly infinite compute, really do this marginalization. There are many different possible steps at each point, and when we start talking about chains of thousands of steps long, this becomes extremely intractable. So figuring out how to actually do this is the fun part of the problem. Before we get into some of the methods, I want to make a quick note about reinforcement learning. As I noted earlier, I find reinforcement learning to be quite a challenging area. There are many different conflicting definitions about how these systems work and how they're actually trained. I think many of the details are actually specific choices that individual companies needed to make in their system design. Many of these things often look quite different in open source than they might do within a kind of big reinforcement learning lab. With that in mind, I think these choices are very important, but for the sake of this talk, I'm going to leave most of them out. There are particular choices about how to batch things, how to do it on policy or off policy, how to use KL constraints to make sure your system doesn't go off the rails. For most of the algorithms I'm going to talk about, though, you can implement them either in a simple way or in the more complex or scalable method. It's not that these details aren't important. When I talk to experts, they say these are some of the most important things to actually learn and make these systems work. It's just that I'm not the right person to tell you about them, and I think there are interesting ideas here without going into these systems in detail. Finally, one last quote from OpenAI that I found really interesting. They said that when training a model for reasoning, one thing that immediately jumps to mind is to have humans write out their thought process and train on that. When we saw that if you train the model using RL to generate and hone its own chain of thoughts, it can do even better than having humans write chain of thoughts for it. That was the aha moment that you could really scale this. I think this quote is pretty amazing. I imagine it was quite shocking for the first time to see the model reason through a problem and get it correct. I don't know, maybe I'm a sucker. Okay, with that background, we can actually get to the suspects for what might be going on here. So I narrowed this down to 4 different suspects: guess and check, process rewards, search or AlphaZero, and learning to correct. These aren't formally different areas, but when reading this literature, I did find it a bit overwhelming. There are many different papers that think about these problems, and, well, everyone's kind of convinced their method is what's really going on. That being said, I found these 4 to be a useful outline for helping me think about this problem. Suspect 1 is the simplest. 3 steps. We sample n chain of thoughts, we check which ones were successful, and then we train on the good ones. If we think about it in terms of our picture, we will independently sample. Some of the chains will go wildly off, and some will reach the solutions. The solution ones are the ones we would like, and so we can train them into our language model. If you're like me, you might find it helpful to formalize what's going on here. We can think about this as a form of rejection sampling expectation maximization. EM is a very traditional algorithm in machine learning, and it's been applied to these sort of reinforcement learning algorithms for decades. We can think of the expectation step as running rejection sampling, as we saw earlier in the talk, and we can think of the maximization step as fitting our language models to the samples that fit with our posterior. The more we run this expectation step, the closer to the true expectations we've calculated, and the better our end step will in getting to the answer itself. Traditionally, EM is done in a batched offline process, but there are versions that are online or that can work with any other form of reinforcement learning. Given the simplicity of this method, it's been discovered and noted to work many times. In NLP, this works as a form of self-training. This is a method that was described in 1995 and later used to produce state-of-the-art syntactic parsers. This method, of course, has different names in different areas. OpenAI refers to it as best-of-n training. A popular recent variant is called STAR, or self-taught reasoning. My formalization is from the paper REST-EM. In some sense, the name here actually doesn't really matter too much. I mostly list them all so you don't get intimidated or think more is going on here than actually is. And high level, all these papers come to a similar conclusion. This method is simple, but it works, and it works pretty well. You can get relatively consistent improvements, particularly in lower samples, across many different problems. If anything, this should be a required baseline in most papers. Of course, the assumption here is that we have access to the verifier. It seems hard to actually scale the test time compute if we only have this during training. Of course, we can try to use what we've produced to also train the verifier. Since we have a lot of samples from rejection sampling, we can further try to train some sort of learned verifier that we can keep around at test time. This idea, which is often referred to as amortization, basically using a learned model to represent some sort of complex system, we can create our own sort of learned verifier at test time. This could then be used as part of chain of thought or for some sort of test time rejection sampling. So is O1 just a guess and check RL system? Well, there's some signs it might be. One thing that's neat is that this approach is extremely simple and scalable. One thing OpenAI has done in the past is just build larger, more powerful versions of things people thought worked reasonably well. We also have seen positive results with this, and potentially with huge amounts of data collection for the verifier, you could get a system like this to work really, really well. What we're missing, though, is that there's no evidence that simply sampling will produce some of the chain of thoughts that we saw earlier. This seems like a big change to just have this happen automatically from our system. In addition, the assumption here is that if we do enough rejection sampling, we'll get some good chains. But for some of the harder problems, this seems really unlikely. This seems computationally efficient or even impossible. So let's build a bit more structure into these systems. This next section is on process rewards. Suspect 2. During chain of thought sampling, we'll have some guidance that we'll both use to learn and to improve our trajectories. We then run the same process where we check if our final or partial versions are successful and train on the good ones. The term process rewards comes from two papers, one from Google and one from OpenAI. In these papers, they learn an early verification model, which they call a PRM or process reward model. They show that learning this intermediate model can improve in rejection sampling compared to a learned model that gets the full solution. The graph on the right compares the learned intermediate model both to majority voting and to a model learned only on full solutions. Note this graph is not making any claim about the learning process, just that we're able to successfully complete more chain of thoughts by utilizing an intermediate learned verification function. There are several ways for acquiring this process reward model. One might simply be to sample trajectories from your model and utilize human annotators to label these. Another approach, which is becoming more common in the literature, is to take partial chain of thoughts from your model and then perform rollouts. These rollouts will tell us how good the chain of thought is at a given time. As we discussed earlier, we can then utilize these rollouts to train a learned process reward model. We'll call this our psi. This will give us a sense of how good we are doing and can additionally be used at test time. There are many ways we might choose to parameterize this learned process reward model. One interesting idea is to learn it as a large language model. The idea here is that the actual process reward model that's checking how well we're doing can itself use chain of thought. It might try to reason about individual steps and utilize them to decide upon the answer. What's important about this step is this is an idea that merges the generator and the verifier. You can have a single model that is both trying to do reasoning and also trying to verify this reasoning. This is an idea that has begun to be explored recently in the literature, where several approaches build these generative verifiers. On medium-scale problems, we can see that this learned process reward style seems to work. In this paper, known as Math Shepherd, they train a model utilizing rollouts. They can show that in this model, they're both able to find better solutions with their learned intermediate guide, and they're also able to learn a final model that's better at math. This approach also brings the full story into a bit more focus. If we're going to use a verifier that is also using chain of thought, and we're going to merge that into a single stream, we can imagine alternating between generation and verification and using that to improve our test time solution. For example, if we look back at one of the chain of thoughts I mentioned earlier, we see statements like, "Is that a good explanation?" ? While traditionally we would think of this as part of the generator, this might be part of a verifier that's been merged into the same model. It can move back and forth between generation and verification within a single language model. So is this O1? Well, there's some evidence that these intermediate guides are effective. It also removes the challenge of just having a single learned verifier. On the negative side, we haven't really seen anything yet that explains some of the advanced planning that we've seen this model do. And we don't really know how to fully do this combination of generator and process reward model into a single chain of thought. It's a compelling idea, but there are a lot of details still remaining. If I had to guess, I would say I personally think this is probably closest to what we might expect O1 to be. It fits with the research papers that OpenAI is publishing and some of the rumors about the simplicity of the system itself. That being said, my confidence is quite low, and a lot of people I talk to think it's something quite a bit more advanced. So let's look at some more search-based solutions. So in particular, let's remind ourselves how AlphaZero works. This was a very important paper in the history of deep learning and RL. In this paper, which was a follow-up to AlphaGo, they demonstrate that a system completely taught with self-play could achieve expert-level performance in a very hard task. At a casual level, the way the system works is it plays games of Go using a complex search algorithm, then trains a neural network based on the trajectories of this system. It then uses that neural network to again play some more games and iterates on this process. This is the canonical example of success stories from very simple RL-based algorithms and demonstrates scaling without the need for extensive expert demonstrations. There are several reasons this system is relevant to the discussion, but one of the more recent ones is this work on alpha proof. We don't have a lot of details behind how alpha proof works, just that it did extremely well at a very hard math competition, and a blog post that says, when presented with a problem, alpha proof generates solution candidates and then proves or disproves them by searching over possible proof steps in Lean, which is a proof assistant. Each proof that was found and verified is used to reinforce alpha proof's language model, enhancing its ability to solve subsequent, more challenging problems. So, if you squint, this does seem rather similar to some of the language we saw in OpenAI's blog. So how might this work? Well, we're going to assume there's going to be some self-play, using some kind of guided search with exploration. We'll then label the final outcomes of these self-play games. We'll train a guide and generator and iterate. The terminology for this in the literature is known as expert iteration. It refers to this iterative process where an algorithm that combines a learned model plus a complex expert search. The goal is basically to distill the search process into the model. We do this by generating lots of samples, utilizing our reward model to improve upon them, and then labeling the good ones. We iterate on this process, retraining both the generator as well as the guide model in order to do better on the next iteration. A popular way to do this with language modeling is to use a search algorithm known as beam search, and then to utilize a guide that will look very similar to our process reward model. Here our guide will tell us how well we're doing by looking at our partial chain of thought so far. Given this guide, we can then perform beam search. The way beam search works is that at every step of the process, we expand out to all possible next chain of thoughts, and then we just keep the top 4 based on how well they're doing from our guide. This will keep around 4 different possible solutions, each of the same length, based on how close they are to producing a good final answer. Of course, there's a lot of details here I'm not specifying. We have to determine how to expand to new possible chain of thoughts, as well as producing somewhat different chain of thoughts that might likely give us a different path. We also have to determine how to weigh the guide versus what the language model thinks is the next path. But at high level, you can see how this expertise can then be trained into the model. Instead of a guide, we might also consider using rollouts directly. In this example here, we are running beam search at each step and using rollouts at training time in order to tell us how well we're doing. Here's our first step, second step, third step, and here's our fourth step. In systems like AlphaGo, these rollouts are combined with a learned guide function. Together, these give us a good sense of the problem, and we learn how much we can actually trust our learned guide function versus explicit rollouts. Remember, our goal at test time is to remove the rollouts entirely. Several recent papers have experimented with using these forms of expert iteration in order to produce good reasoning systems. Again, we're working on somewhat more medium-scale math problems, but there is some preliminary evidence that there are significant benefits from doing this form of search. Specifically, we see large increases in accuracy compared with doing the naive guess and check system, here represented as star, that we saw earlier in the talk. While beam search is a common approach for efficiently doing search with language models, systems like AlphaGo used much more complex forms of search for game playing. In particular, the famous search algorithm used in those papers is known as MCTS, Monte Carlo Tree Search. This is a complex algorithm that combines search with exploration. The way it works is that for a given math problem, we're going to start at the beginning. We're then going to walk down our tree until we hit a leaf node. When we get to that node, we'll expand 5 possible next steps. So in our case, that node will consist of a partial chain of thought, and the next 5 steps will be 5 other expansions of steps we could try next. We'll then pick one of those at random. When we get to that step, we'll do a rollout of the next steps in the chain of thought. Depending on whether these were successful or not, we'll then update all of our parent nodes based on the fact that we ran that rollout and also how well it did. We can continue this process, growing our tree and applying different rollouts. The key to the algorithm is that we are not simply just trying to reach the end as fast as possible, but trying to explore different parts of the tree. Let's look at a demo. So in this example here, we have run our selection process and gone down the yellow nodes of the tree. We then look at the bottom node, that chain of thought of 3 steps, and we expand it to 3 next possible steps. Here we can see the expansion, and the yellow node represents which of the expansions we pick to roll out. We then run our rollouts here. I'm showing 8 independent rollouts, several of which reached the solution and several of which did not. Based on this rollout, we then update the node and all of its parents to tell them how well it did. Okay, now we start the process again. We now need to select which node to expand next. We've chosen a different set of nodes to select, and we've reached a different leaf. This selection process is based both on which nodes won and which nodes were not yet explored. We then expand this node, and we do another set of rollouts. Based on the success of these rollouts, we then update each of the parents. As mentioned earlier, the main benefit from this process is that when we do selection, we are basing that selection both on how well these nodes did and also how well they were explored. The benefit here is that we can explore many different possible chain of thoughts and try to find ones that we may not have explored in the past. So is there some type of search algorithm being explored in O1? Well, it fits with the history of major demonstrated results in RL. And it's a particularly nice way of adding more training time into the system. Remember, we know that O1 is data efficient, but they may have used an incredible amount of compute in order to do training. Furthermore, given that the chain of thoughts that we actually are seeing from O1 look a little bit like search with properties like backtracking or high-level outlining, it's plausible that those came into the model through something like training time search. However, there are some negatives to this process. It's much more complex algorithmically, and it's costly to maintain open states. Compared to the first 2 systems, it does seem much harder to scale. Additionally, we don't see anything about doing this sort of complex training tree search in any of the OpenAI release material. The other thing that's interesting is that there are a lot of papers kind of exploring MCTS for language modeling, but at least in the open research community, we haven't seen too many successes. It seems like simpler methods work a bit better for these problems. Our final method is learning to correct. So to motivate these algorithms, I want to note some of the differences between game playing and language. In game playing, there is a set of fixed moves, and the main source of exploration is to just explore these alternative moves. In language, there are really a lot of possibilities. You can get around some of this by sampling or fixing the next possible steps you might take. But I think actually a lot of the exploration should be in this process itself. How you determine what are different next chain of thoughts, which ones will cause more exploration or cause more backtracking. This motivates a series of methods on learning to correct. At a high level, we're going to start with some failed chain of thought that came from our system. We're then going to do some sort of search to find successful corrections of this failure. Based on this outcome, we're then going to train on the entire process, not just the correction, but the original as well. A motivating example is work on self-correction. The idea here is to isolate pairs of chain of thoughts. We'll call one Z prime and the other Z double prime. These chain of thoughts are similar, but one leads to a correct answer and the other does not. If we can isolate these two, we can train a model that can improve upon Z prime in order to move more towards Z double prime. If we can do this at scale, we can hope to build this ability into the generator itself. This approach sounds simple, but it actually has lots of challenges in practice. One issue is that the model will often just collapse. If the first chain of thought was just not very good, it'll learn to ignore it and simply just directly try to generate the second one. The other issue is that you have to be extremely careful of distribution shift. If you collect a lot of examples, but they look different from what your model's actually generating, it might not actually self-correct in practice. It'll learn about your examples, but not about what your model actually produces in mistakes. One approach to get around this issue is to try to be as on policy as possible. In this setting, we will generate our z prime and then take all possible continuations from z prime to the goal. We will fix the model's original output and try to learn what the correction would be from that given point. There's some subtleties in getting this right. For instance, in the paper listed, they first run a training round where they only learn the correction part of the model. Then, in a second stage, they also learn the original part of the model itself. This is done to ensure that as the first part of the model changes, the correction part learns to adapt and continues producing good corrections. When done correctly, this approach beats both training on examples as well as our guess and check approach. It also scales better than simply pairing up examples and learning to correct from them. Of course, our final goal is not individual corrections, but corrections applied repeatedly, all in a single chain. This is the motivation behind stream of search. In this work, they first find an optimal z-star. They do this by applying a training time search algorithm that produces the tree on the right. This tree finds a very good chain of thought, but also intermediate branches that go off in the wrong direction. Once we have this tree, though, instead of training just on the path to the final answer, we're going to instead linearize this tree into a single stream. The picture on the bottom shows schematically what's happening. We're basically going to template construct a synthetic chain of thought that goes in windy roads to get to the final answer. When we see actual backtracking in the tree, this will become words in the stream. This gives us something that looks like it's doing search, even though it really is just a single path from the start to the end. We can then train on these streams in order to get search-like behavior. To summarize that a bit more informally, we're going to try to convert from a tree to a stream. We do tree search to explore multiple paths. We'll convert this stream as a linear sequence, and then we'll allow models to see their mistakes in the stream. This sort of method might be combined with methods like learning to correct in order to make each individual step better and more on policy. This approach is relatively complex, but a lot of experts I talked to were convinced that something like this is behind what O1 is doing. So let's discuss the pros and cons. It seems like learning to correct and plan is a pretty important part of the process. It's the first time we've seen something that looks similar to what the actual chain of thoughts from O1 do. It also seems plausible that this can be used to induce search-like behavior into a single test time model. On the negative side, this is also quite a complex training procedure. There are many parts where the system could fall apart or collapse. This is because these corrections require giving synthetic examples or trying to keep the model on policy. We also have limited empirical evidence so far in the open research literature that this can induce this sort of interesting behavior. In particular, methods like stream of search have only been applied on relatively simple problems. Still, I think this is the most interesting of the potential ideas, and it would be really cool to see people build this in practice. Let me conclude by talking about some of the implications of this research. So first off, the thing I care about most is actually replication. As an open source community, we need to get better at building some of these large-scale RL-based systems and showing they can really work. It's critical to have open source versions of these models so that we can explore what's going on and to build better or more efficient ones. There are critical system aspects that differ for how open source systems might look versus how the ones at companies are designed. And so it's quite possible the open source versions may not actually look the same or maybe perform in different ways. Still, even if we can't replicate exactly what OpenAI did, I think the fact that they demonstrated this result really should motivate the community to know that it's possible and that we can build one of our own. In addition, there are incredibly exciting research implications behind this work. I want to talk about a couple areas that I think it's important to consider. The first is that the last 5 years have really been dedicated to this idea of understanding what scaling means and how it changes how a language model performs. Much of this has been somewhat mysterious. These abilities come out of these models as we go. I'm really excited to understand how test-time compute can be understood and how it changes some of these stories. Test-time compute seems much more transparent. We can understand what the chain of thought is doing and to get a sense of how it explains or contradicts the results it produces. The other thing that's quite interesting is the fact that these systems are bottlenecked by their inference time systems capabilities. We've been focusing on inference to try to make it cheaper or faster in a kind of chatbot setting. But in this setting here, inference really becomes prioritized. If you can make a system 1,000 times faster, that's, say, 3 orders of magnitude of extra reasoning ability. That's a much more interesting capabilities change than simply kind of serving a model cheaper. Another thing I'm really excited about is just to be done with prompting. I think prompting has been an intellectually really kind of boring area and one that has kind of dominated the practical use. Don't get me wrong, I think prompting is really useful and there's a lot of cool things you can do with it, but there's not much more to say about it from a research perspective. I'm really interested in the move from prompting to some sort of formal specification. If we can produce interesting verifiers for hard problems and use language models to optimize against them, that opens up all sorts of interesting new areas of work. Next, I think these models really open up many new paths for evaluations. My group has been thinking a lot about evaluations that are just extremely hard and on tasks that we'd really like to do, but are way beyond the capability of even the best language models. For instance, we've been working on benchmarks where you have to write entire new coding packages based just on their unit tests. This sort of superhuman evaluation becomes really exciting when you can have a model that just runs forever and takes that feedback into account in terms of producing an answer. I think we really need to think about evaluations in terms of what we'd like these systems to do, as opposed to just what we think the current generation can do. And finally, maybe this one is obvious, but throughout this entire talk, I never really talked about neural networks at all. The move to search-based systems really is about how these systems are utilized, what they generate as their intermediate steps, and how you might change or explore that. This is very different than the sort of interpretability that we've seen where you try to dive into the model itself and interpret its kind of continuous valued weights. I'd be really excited to see how this changes how we think about this problem, how we understand our models, or what they do. So thanks very much for listening. I have a GitHub page with the full bibliography, slides, and issues from this talk. I'll probably update it for the next couple months as new papers come out or come in. If you have any thoughts about where this is leading research, please leave them in the comments or on the issue page, or you can find me on Twitter. Thanks so much.